Hello everyone, it's my great pleasure and great honor to introduce Dr. John Clauser. John Clauser received his BS in Physics from California Institute of Technology in 1964, his MA in Physics in 1966, and Ph.D. in Physics in 1969 from Columbia University. From 1969 to 1996, he worked at Lawrence Berkeley National Lab, Lawrence Livermore National Lab, and the University of California, Berkeley. John was awarded the Nobel Prize in Physics in 2010 and the Nobel Prize in 2022, together with Alain and Anton Zeilinger, for their observations of non-local quantum entanglement and experimental test of local realism. In 1969, with Michael Horne, Abner Shimony, and Richard Holt, inspired by theoretical results from John Bell, he proposed the first test of local hidden variable theories and provided the first experimentally testable CHSH-Bell theorem. Prediction for these theories. The Clauser-Horne-Shimony-Holt CHSH inequality. In 1972, working with Stuart Friedman, he carried out the first experimental test for the CHSH inequalities prediction. This was the world's first observation of non-local quantum entanglement, and was the first experimental observation of violation of a Bell inequality. In 1976, he carried out the world's second experimental test of CHSH inequality prediction. In 1974, working with Michael Horne, he formulated the theory of local realism as a generalization of local hidden variable theories. The first showed that a generalization of Bell's theorem provides severe constraints for all local realistic theories of nature. And that work introduced the Clauser-Horne CH inequality as the first fully general experimental requirement set by local realism. It has only recently, in 2013, has been tested experimentally. He also introduced the CH non-enhancement assumption, whereupon the CH inequality reduces to CHSH inequality, and whereupon associated experimental tests also constrain local realism. In 1974, he made the first observation of sub-Poissonian statistics of light via a violation of the Cauchy-Schwarz inequality for classical electromagnetic fields, and thereby first experimentally proved that photons can behave like localized particles and not like brief pulse of electromagnetic radiation. In 1987 to 1991, he proposed and patented atom interferometers as useful ultra-sensitive inertial and gravity sensors. In 1992, with Mattis Rinch, he first deduced the number-theoretic properties of the functional Talbot effect and invented the Talbot law interferometer. In 1990 to 1997, with Shifan first used Talbot law interferometry to build an atom interferometer. In 1998, he invented and patented use of the Talbot law interferometry for ultra-high resolution interferometric X-ray imaging. This invention, in turn, allowed X-ray phase construct medical imaging of soft tissue. His talk today is on, the keynote address is on experimental proof that non-local quantum entanglement is real. Please join me to welcome Dr. Clauser.
Let's see, it is quite an honor to be actually back here where I first learned quantum mechanics. I was an undergraduate here, class of '64, and so I will start out by does this work? No. This does not. I use it over here. Okay. All right. Okay. No, it doesn't work either. No. Where? I tried to. Okay.
Okay. All right. Here's what I learned at Caltech. When I first learned quantum mechanics, every quantum mechanics textbook you read begins by introducing Schrodinger's equation. Actually, it's Schrodinger's first equation. It's a wave equation that describes a complex valued wave function, psi of r, a position vector and time. It propagates in space-time. Its absolute square, psi star psi, describes a so-called probability density, which also propagate correspondingly as waves in space-time. When you multiply psi star psi times charge or mass, it gives the local charge or mass density of a beam, particles in a beam of non-interacting particles. When you apply Schrodinger's equation to hydrogen, it describes standing waves that are standing around the nucleus of the atom. It has a set of discrete solutions called eigenfunctions. These describe the allowed energy levels, the so-called and previously mysterious stationary states of hydrogen and of other atoms. Its general solution is given, the eigenfunctions of that are essentially the number of waves, standing waves you can sort of wrap around a nucleus, if you will, corresponding to each stationary state. The general solution is a superposition or a sum of these eigenfunctions. Actually, most of my career here at Caltech, I spent calculating eigenvalue problems of every shape and form. I figured how does one calculate eigenfunctions, etc. This is a major part of the education of learning quantum physics. The one notices that if this probability density, if say for example an atom is in a pair of superposition of two states, the charge density oscillates, and sort of very much like an electric dipole antenna, and correspondingly radiates energy at the beat frequency between the oscillating frequencies of the two states. Moreover, Max Born noticed that if you calculated what is called Born's conserved probability current, it's essentially psi times the velocity operator psi star velocity operator that acts as a conserved current serves probably what he referred to called a conserved probability current. It flows in space, and he used it to demonstrate flux conservation for Rutherford scattering. Okay, since it did all of this great stuff, it was an instant success. I hope people here don't disagree with that. And if you do, you are suckers, because I hope by the end of this lecture, I will make you very nervous by believing this. It starts out, okay, Schrodinger actually developed not just one, but two equations. First one describes hydrogen, which is a single particle equation. And later on, described a second one that describes helium. It's typically, you don't find it until you get to late chapters in quantum mechanics textbook. He found this was required for multi-particle systems, for greater than 2 particles. Hydrogen only had a single particle. So for multi-particle solutions, he discovered that there are quite unexpected solutions. Schrodinger invented the term quantum entanglement to describe these unexpected solutions. Okay, so the wave function of a single particle is just a sum, a general solution is a sum of all of the eigenfunctions. And if you have 2 independent particles, each one has an individual wave function, it's the sum of its eigenfunctions. But the general, but that's only if they have never interacted and are not entangled. Once they become entangled, there are additional solutions which consist of a sum of products of the eigenfunctions. So if 2 particles are entangled, they exhibit an intimately correlated behavior. If they don't need the particles, there's sometimes confusion. Particles do not need to be identical to be entangled. In fact, in my first experiments, we were entangling green photons with violet ones. Okay. And if they have never interacted, they remain unentangled. But once they have ever interacted, they become entangled. Now, von Neumann, in his textbook, Mathematical Foundations of Quantum Mechanics, pointed out that the only way you can get rid of entanglement is by the measurement operation. Okay, so let me move on. Let's see, that was this one. Okay, so what does all this mean? Well, what is this intimate correlation I'm talking about? Within a helium atom, you have the 2 electrons are in intimate contact, overlapping each other. So wave functions are overlapping each other. So it's hardly surprising that their behaviors are intimately correlated. But Einstein and Schrodinger, both independently, noticed a very peculiar feature of quantum entanglement, that no matter how far apart you separate the 2 particles, if they're entangled, they remain entangled. This was very disturbing to both Einstein and Schrodinger. So much so for Einstein that Einstein, Podolsky, and Rosen proposed that quantum mechanics perhaps is an incomplete theory that requires additional variables to explain this intimate correlation or the for non-local entanglement. And following Einstein, Podolsky, and Rosen, Schrodinger and Fury independently hypothesized that maybe something's wrong and that entanglement disappears if you separate the particles very far. But since that hypothesis changed predictions, it obviously had to be wrong. So they dismissed it. Niels Bohr argued that hidden variables are unnecessary. And Einstein said, "Oh, you're just playing with words," is effectively his response. I believe that. And the debate between the two was never really fully resolved. And I will get to that much later in the talk. Okay, so prior to my work in 1969, while I was still a graduate student at Columbia, the spectrum of helium was, and other multi-particle systems, was overwhelming, considered overwhelming evidence that entanglement is required to be part of quantum mechanics. Prior to my work, nobody even suggested doing an experiment to test non-local entanglement. There was one exception with Bowman and Aharonoff, 1957, showed that the Wu-Shaknoff experiment, that was a polarization correlation experiment for gamma rays emitted in positronium annihilation. They suggested that that was a suitable test for the Schrodinger-Furey hypothesis that entanglement disappeared. Okay, so what is a Bell inequality? There are actually three of them, actually, probably more, but the three important ones. The first one was in 1964 when John Bell was trying to understand this Einstein-Podolsky-Rosen paradox. It was of immense importance, especially for me. It showed that the Einstein-Podolsky-Rosen argument, looking for hidden variables, leads to exactly the opposite conclusion that Einstein, Podolsky, and Rosen came to. They had Einstein, Podolsky, or Einstein, Schrodinger, Bohr, Bell, like everybody else, assumed quantum mechanics always gave correct predictions. And you will see later why, but no experimentally testable prediction was made. So then my associates, Mike Horne, Abner Shimony, and Dick Holt, and I, well, this is while I was still a graduate student. Mike Horne and Abner Shimony are at Boston U, and Dick Holt was a grad student at Harvard. Came up with the CHSH inequality. Unlike Einstein, Schrodinger, Bohr, Bell, we did not automatically assume that quantum mechanics makes correct predictions. This was heresy. We proposed a detailed experiment to actually test this bizarre prediction. Because we found we had a different prediction from quantum mechanics. And the question is, which one does nature choose? And then in 1974, Mike Horne and I were trying to understand, what have we really proven here? And we found that we generalized hidden variable theories to cover virtually all of Einstein's platform for doing physics, including general relativity, by the way. It's the resulting theory is what's called we call local realism, and we produced a new inequality, allowing it to be tested. And it is the first loophole-free inequality. I mentioned that we committed heresy. At the time, it was highly politically incorrect within the physics community to even question the foundations of quantum mechanics or propose such an experiment. On my graduate faculty at Columbia, when I was a grad student doing this, everybody universally told me that doing this experiment would totally ruin my career. Bob Serber, who basically designed the atomic bomb at Los Alamos, said, "Oh well, it might be worth pointing out, but no decent experimentalist would ever do it." When I was actually performing the first experiment, I was here at Caltech and had an appointment with Richard Feynman, who he was totally outraged. He was literally offended that I would try to test quantum mechanics. He threw me out of his office and he said, quantum mechanics needs no further testing. Okay, we can start with the Bell's 1964 inequality. Okay, again, Bell assumed that quantum mechanics always yields correct predictions. He considers the predictions for measurement results performed on separated spin-half entangled particles from Bohm's 1950 Gedanken experiment, a thought experiment for the EPR paradox. And like I said, with great irony, he showed that EPR's argument led to the exact opposite prediction that they had come to. That showed that the intimate correlation between the two particles cannot be explained by hidden variables. Unfortunately, his proof required a totally impossible to achieve condition, so no experiment was really possible with his 64 quantity. So this is the experiment that Bohm is in his 1950 textbook, Quantum Theory. One of the great discoveries early on in quantum mechanics was spin-and-a-half particles. Spin-and-a-half particles that have two states. And more importantly, Stern and Gerlach did a marvelous experiment where they took, let's see if I push this. Yeah. Okay, if you put a beam, make a beam of spin-and-a-half particles, and you put them through an inhomogeneous magnetic field, strong field gradient, the beam splits into two independent beams. And this corresponds to the doublet spectra that you see in, for example, on the first column of the periodic table. So the beam particles will diverge and either go into, say, an upper slit or the lower slit. And in this example, it would trigger a detector to have give the value plus or minus 1. So what Bohm suggested was, suppose we have a spin 0 molecule, spherically symmetric, and it dissociates into pair of spin-and-a-half atoms, and these then propagate in opposite directions into two Stern-Gerlach apparatuses. Okay, and as I've drawn here, these could be rotated about the flight axis of the particles. Okay, so you can ask, well, what's the average value of the product of the results? Well, for conservation of angular momentum, if the first goes into spin up here, it'll go into spin down over here. So product is always a -1. Since it's spherically symmetric, it doesn't really matter how you rotate the pair. It only depends on the angle between the two polarizers. Okay, so here is the expectation value. Okay, the one's straightforward to calculate using quantum mechanics. It's minus A dot B. Polarizer orientations. Depends on the angle between the two. And so here is that first point I gave you here. And in Bell's proof, he required that you have a perfect correlation and always pass through this point. And if it didn't go through that one point, the whole proof fell apart. If you say you flip one of the analyzers 180 degrees, that just interchanges the plus and minus one on one that analyzer, and so the plus one, the minus one switches to plus one. And if it's they're say at 90 degrees to each other, then if it goes into spin up on one side, then half the time it'll go into spin left, half the time spin zero. So the average value of the product is going to be zero. Okay, and correspondingly, you get the cosine curve from the A dot B. What Bell showed was that for any hidden variable theory, where the two sides cannot communicate with each other, that you could not get this cosine curve. The best you could do is get this triangular function. Totally amazing result. It's effectively a difference between an interference pattern and a moire pattern. Moire pattern is a convolution between a pair of step functions, and that's what gives you the triangular function. Okay, so Mike Horne, Abner Shimony, and Dick Holt and I looked at this, and we were unlike others before us. We did not automatically assume that quantum mechanics always gives predictions. As I commented, Rucher's total heresy. And we were inspired by Bell's theorem to actually wonder, well, okay, which okay, right. Which prediction does nature choose? So we actually designed a very specific experiment. We reformulated Bell's original 64 inequality to a new form, which did not have that special point required. It wasn't so obvious you could do that, but we figured out how to do that. And so we still have an inequality that makes different predictions for quantum mechanics and for local hidden variable theories. I call them local because there's no way, they assume no communication between the two apparatuses. Okay, so we have two different predictions. Which one does nature actually choose? Let's do an experiment. There were a few other minor details along the way. We'll go into those now. Okay. So then finally, Mike Horne, the third inequality talking about was Mike Horne and I were trying to understand, well, what does this really mean? What all is actually being tested here? And we, in the process, invented what's called the theory of local realism. It's a very general theory, far more general than EPR's hidden variable theory. It underlies virtually all of Einstein's framework and platform for doing physics, including general relativity. example. So for this more general theory, I will go on later on describe it to you. We formulated a whole new inequality, the CH inequality. It allows totally loophole-free experiments to be performed. And with very mild auxiliary assumptions, the CH inequality reduces to the CH-SH inequality. And it has only recently been tested. Okay, did I skip one? Okay. So here I want to describe 4 different experiments that I performed back in the early 70s. Those were all 50 years ago. The first one, after I got my degree at Columbia, I went to Cal Berkeley and worked with Stu Friedman, a graduate student, and we performed the first test, that experiment that the CH-SH paper outlined in detail. And this was the first experimental test of a CH of any Bell inequality, and it disproved the whole class of local hidden variable theories. Then, well, it turns out at Harvard, they did, Richard Holt was doing an experiment, a similar experiment, and they got the opposite result. So I then repeated their version of the experiment in 76 and got the same result that Stu and I got in 72. And while I was at it, okay, so if the 2 photons have their linear polarizations correlated, it turns out they also have their circular polarizations. They don't have any polarization defined before a measurement is concerned, so that they should have a circular polarization. So that was a rather amazing prediction also. So I actually tested that in 76. And then finally in 74, it's not really does not a test of a Bell's inequality, but it was a test of basically of a disagreement between Einstein and Schrodinger on whether or not photons behave as real particles. Okay, this is a picture of the 1972 experiment in sub-basement of Burge Hall at Cal Berkeley. Here's Stuart Friedman, a young graduate student working on it. This became his Ph.D. thesis project. What we did was we measured the linear polarization correlation of pairs of photons that were emitted in a cascade decay. We go from a J equals 0 to J equals 1 to J equals 0 state, emitting 2 photons in the decay. And that was of calcium atoms. The calcium was in an atomic beam. This is a small atomic beam apparatus here. You can't put it in a bulb because it'll etch all the windows. You have to keep it in a very tenuous beam. There are a lot of other experimental tricks we had to deal with. One of the biggest problems we had was that tunable tunable lasers had not yet been invented. Steve Drew was down the hall trying to build one for his Nobel Prize winning work. And he didn't finish his degree till after I had finished total of 4 experiments. So anyway, so we got a 6 sigma plus violation of Bell's inequality. At Cal, we were under the thumb of Louis Alvarez, who had set the standard for doing physics experiments is 5 sigma. Thou shalt not consider it conclusive unless you have a 5 sigma result. So he got 6. Okay, so like I said, Nick Holt had gotten the opposite result, so I decided to repeat his experiments. Stu got his degree, went off to Princeton, and so I rebuilt the whole system to use a mercury source. This had mercury vapor with in a separated isotope of mercury 202. You couldn't have any nuclear spin, otherwise it would depolarize. So this was a 3-level cascaded mercury. There was an electron gun out of a cathode ray tube to excite the beam. And there I only got 4 sigma. It was a tougher experiment. But while I was at it, I put in quarter wave plates and actually measured the circular polarization. Okay. Now while I was there, I used my brief opportunity to do experimental. I mean, again, this was all very, I was doing heretical work and not particularly popular, but somehow suckered the Cal faculty into allowing me to stay. And I wanted to test that whether or not there is a wave particle duality for photons. It turns out it had never been demonstrated experimentally. Einstein, in 1917, a very famous paper in which he derives the A and B coefficients, showed that particles, that photons emitted and absorbed must behave as what he referred to as directional energy bundles, also known as photons. He did this for the thermodynamical argument. If you have a Planck radiation interacting spectrum interacting with gas of atoms or molecules, in order to get equilibrium, you had to have photons emitted in directional energy bundles. Now, it wasn't immediately clear what does this mean? What is a directed? Well, it also had to have the momentum in a highly directed position, but it wasn't clear. Could this be just a classical pulse? Oseen came up with solutions to Maxwell's equations that showed what were called needle radiation. Wasn't clear that it was really, that these were really particles. Now Schrodinger, actually, this is where the old Schrodinger interpretation was the oscillating antenna that I mentioned earlier. Could they just simply emit pulses, classical radiation? So he asked the question, well, do they really act like particles, which you need particles in order to get pointwise conservation of energy? So he suggested, well, what's the difference between a wave and a particle? You suppose you put a wave into a half-silver mirror. If it's a classical wave, half of it will be transmitted and half will be reflected. Whereas if it's a particle, it will either be reflected or transmitted, but never both. So he suggested, well, suppose I put 2 photomultiplier tubes on opposite sides of a half-silvered mirror. If it's a wave, I should sometimes see coincidences if I put a single beam of single photons through. If it's particles, I will never see anomalous coincidences. So he goes down from Vienna down to Budapest to his friend Janissy, who actually performed the experiment. Unfortunately, Janissy did not worry about the detector efficiencies on this, and it turns out his experiment, if you look at it carefully, was insufficient by about a factor of 10 to the 6. So it was totally inconclusive. So I said, well, okay, I could do that. We had just, Sue and I had just developed single photon sources in these cascade. So what I did here was I did the experiment twice. I have a source of those same experiment source I used for the mercury cascade experiment. Okay, and did the half silver mirror trick twice. So I sent it through one beam splitter, a pair of photo tubes, sent it the other decay product, the cascade through second beam splitter, and now the additional trick used was that Roy Glauber had just come up with a new analysis of fluctuating classical electromagnetic waves. And what I found was that you could take the Cauchy-Schwarz inequality straight out of Apostles' calculus book and apply it to his formulation and show really an amazing result that, okay, so you should see real coincidences from here on both sides from the cascades, but you should not see anomalous coincidences between the two detectors. So what I found was that the product of the two anomalous rates had to be bigger than the product of the two possible cascade rates. So I did the experiment, and it must have been 50 sigma result showing that yes, there are no anomalous coincidences. Okay, so too bad this cuts off the, okay.
Please leave the question for the end of the talk.
Yeah, okay.
We can answer the question.
Okay. All right. No, it just keeps. Anyway, I'm out of control. You're controlling. Okay, so Mike Horne and I were trying to figure out what had we really discovered. We came up with what we call objective local theories, and with additional contributions from John Bell and from Abner Shimony, we developed what we called theory of local realism. This is a very general theory. It's a significant generalization of local hidden variable theories, and it's the basic foundation and framework pretty much of what Einstein's whole platform for doing research. Unfortunately, local realism was a very short-lived theory. It was dead on arrival because it had already been disproven by the Friedmann-Clauser experiment and by 76. So even though it was dead on arrival, that wasn't good enough for most people. People wanted to get rid of all the loopholes, and the CHS inequality did that. So let me move on to what does local realism actually say? It's a very general, simple theory. Zeilinger, Anton Zeilinger, my co-laureate, noted that if Bell's theorem and local realism had been formulated prior to discovery of quantum mechanics, it would have immediately been adopted as a law of nature. It's just so reasonable. Okay, so, and from this, we can derive the CH inequality as an experimental test. It does not require causality, and it does not require particle-like behavior. Okay, so what is it? What does it assume? It assumes that nature is made out of stuff. Nature's made out of matter, stuff that has intrinsic properties, that's there whether or not we look at it. We assume that it exists. We assume that it's distributed throughout space. Okay. Einstein, Podolsky, okay. Rosen called it elements of reality. John Bell called it local beables. Cosmologists simply call it matter. Okay. The Bible identified and assumed that it exists, called it light mingled with the firmament in Genesis. Okay. Mike Horne and I called it objects, subjective stuff. It's stuff you can put in a box. What's a box? I'll go in more detail in a minute. It's just an imaginary closed surface. Gauss discovered that there's such closed surfaces exist that divide space into two regions called the inside and the outside of the box. So, and you got to pass through the box to get from the inside to the outside. So, like, say, this is a very general theory. Einstein, his general relativity is far more restrictive. It assumes that the stuff or matter or whatever it is has a finite mass energy density that in fact controls the geometry of the world. He also, we know the local realism allows, is far more general, allows, doesn't require that. General relativity also assumes that the evolution of stuff is deterministic. We're very happy in local realism to have a totally stochastic evolution. We assume that the stuff within the box has properties, and that when you do an experiment in the box, you're measuring the stuff, and that all that happens is that the stuff simply influences the property, the probability of the result you get. Very general. We aren't saying it determines the result. All it has to do is just somehow influence the properties. And we also assume, since it's definite stuff, it's matter, we assume that real results occur, whether or not you're looking at them. So here we're eliminating a lot of Bohr's mysticism creeps in, and Schrodinger's reduction to absurdity argument with the Schrodinger cat. We assume that, for example, you're all probably all familiar with Schrodinger the cat. We assume the cat is either alive or dead. We just don't know which. Okay, I mentioned a box. What's a box? Well, a box is just a closed Gaussian surface. That's a 3D box. To make it a four-dimensional box, for example, here I have a pair of boxes. The boxes are shrinking at the speed of light. And so here we have, here's all you need for the CH inequality. Here you have, here's Alice. Well, I drew this slide before Alice's gender had been, so I apologize, or whatever. Maybe Alice was trans, I don't know. So we have, here we have a box. Here we have another box with Bob in it. Okay, Bob is, Alice is setting an apparatus parameter, which will presumably affect the result, and she will get a plus or zero result, 1 or 0, and Bob similarly will get do the same thing over in his box. Okay, and these boxes are space-like separated, so they can't communicate. And so if I draw an XT diagram, okay, here we have the boxes shrinking at the speed of light. Any correlation that you observe has got to be due to communal stuff back here in this region of space time. Okay, so we suppose, so what does it actually predict? Suppose we have these two widely separated boxes. Each contains a matter. And all we need to further assume is that this parameter choice that Alice and Bob were making in the boxes cannot affect the experimental outcome in the opposite box. So here is where we prohibit Einstein's spooky action at a distance, that there is no faster than light communication. The grand surprise is these very simple assumptions are sufficient to generate an experimental prediction, which is the CH inequality. The experiments were very similar to what I did back in 72. We did not have anywhere near the technology in 72 to test this, the CH inequality. But it has been tested more recently, actually simultaneously at 2 different laboratories. One was Anton Zeilinger's lab in University of Vienna. And the second tests were at Paul Kwiat's lab in Urbana-Champaign, University of Illinois. And they published pretty much parallel results, and both demonstrated. Okay, so the first group, they were not outside, space-like separated, but in the second group, they were outside of each other's light cones, as I showed in the shrinking box. And so what this says is that Einstein's whole platform of study is wrong. I found that rather disturbing because I was a grand fan of Einstein. Okay, so here's one simple application. What does this say? How could this be used? Well, what's the simplest possible object you could consider? It's a single bit of information. Okay. And the question then is, are there objects that you can't put into a single box? Okay. Yes, they are. They're called qubits. They are not, may or may not be classical objects. The CH inequality, when violated, shows that such entities do exist that cannot be put into a single box, but can be distributed into 2 widely separated boxes. This is sort of one of the fundamental premises in quantum information theory. And the refutation of local realism by the experiments shows that such objects provide can be used for quantum cryptography. Okay, that was actually done by Zhang Pan in China for for practical application. Was the Chinese Missis satellite. Uses its configuration is almost identical to that of the original 72 Friedman Clauser experiment, except for the immense separations. Here we had ended up having, I think this is probably the record, we had the two photons remain entangled for detections more than 1,000 kilometers apart. So we have the satellite, which projects entangled photons to two ground stations. You have random polarizer measurements at the ground stations. It's very similar. The configuration is very similar to the picture I showed earlier of Alice and Bob setting their apparatus settings. In 1984, Bennett and Broussard showed that these measurements, coupled with a public communication channel, an openly public and therefore hackable channel, could be used for encrypted communication between the two ground stations. So this is useful for quantum key distribution. And one of the great values of using entangled photons is that you can do a CHSH inequality verification to show that that there is no eavesdropping that occurs. Okay, now here's where I hope to make you feel very, very uncomfortable. Recall that Schrodinger produced two very different equations. One that describes hydrogen, one electron, one that describes helium. The second equation had unexpected entangled solution. Entanglement cannot occur for the first equation. It's only one particle. There's nothing to entangle with. And until now, actually, for papers that I published in 2021 in honor of Mike Horne, who got hit by a truck and killed. This is what is effectively an elephant in the room that has been hiding in plain sight for more than 80 years. These two equations are formulated in very different spaces. And the linkage between the two is what I refer to as Born's ambiguity. It was Born, as far as I can tell, was the inventor of this idea. He invented also Born was the man who invented psi star psi as being the probability density. Okay, so here I will reveal to you what that elephant is. Okay, so the EPR argument fostered two very different schools of thought that persist, believe it or not. And I will give you an alternative to Bohr-Einstein discussion. They persist today in two different sets of textbooks, believe it or not. They bring to, surprisingly, the two sets of textbooks have incompatible formulations of quantum mechanics. School number one is essentially local realism. It follows the single particle notion, that I remember in my first slide, I described to you what quantum mechanics was supposed to be to make it very understandable. And these textbooks all try to make quantum mechanics understandable. I will show you that it is not. That's why I have been confused my whole life. Okay, the first set of textbooks, the first earliest one was by Max Born himself. First two versions were in German. 69 was an English translation. Feynman, in his original space-time approach to quantum mechanics, reviews of modern physics. Here he was doing a space-time description in the title. Schiff, one of the earliest quantum mechanics used at Stanford, very clearly is in this school of thought. French, I used my sophomore year, Physics 2C, here at Caltech. Dickey and Whitkey, my senior year, Bob Christie taught quantum mechanics out of. Bob Dickey was one of the brightest guys I ever met. It was at Princeton. It was used both, so that textbook was used both here and at Princeton. Okay, Merzbacher, very famous quantum mechanics textbook. Eisberg used at Cal, and Isley, Feynman and Hibbs later, and French and Taylor, very important textbook, very popular, used at MIT. Okay, what is it? It formulates quantum mechanics for one particle systems in laboratory space. First of all, what is laboratory space? Laboratory space is a three-dimensional space in which we live. It has three and only three visibly real dimensions. The very important feature of lab space is it exists independent of what you put in it. Say you put in a mixture of hydrogen atoms, helium atoms, hydrogen molecules, etc. Each one has a different numbers of degrees of freedom that are required to set it, but nonetheless, laboratory space has only three dimensions. And so the existence of particles does not change the form of lab space. It has very important geometrical properties that we also learned here at Caltech. Green's theorem, Gauss's theorem, Stokes' theorem, all from vector calculus. There is a vector, R lab, that could be used to define every point in your laboratory. Okay, so the probability density multiplied is gives you the local mass or charge density. This is on my first slide, if you recall. I'm just re-quoting that, and you all bought into that, or nobody seemed to shout me down. Okay, so we have Schrodinger's wave function, which is a function of space-time, the position in the lab. Okay, and the psi star psi gives you the probability density at that point in the lab. These, and perfectly arbitrarily, they can be different everywhere in space. Okay, the evolution of by Schrodinger's equation of this wave function describes probability waves propagating through one's laboratory, and currents, probability currents, as Born invented. Unfortunately, one cannot use this interpretation to describe multi-particle systems. It cannot be used to describe entangled particles system. Okay, the second school of thought tends to be mostly applied quantum mechanics textbooks, some very important textbooks here. Probably one of the most important was by Beta and Salpeter, quantum mechanics of 1 and 2 electron systems. Everything you ever wanted to know about the spectra and structure of hydrogen and helium is in there. When I was at Cal, much of the atomic physics group was testing a lot of the predictions. Bjorken and Drell, relativistic quantum mechanics and quantum field theory. Conan and Shortley, this was the standard reference on atomic spectra. If you want to learn how to use the Einstein A and B coefficients, or how to do Heisenberg's matrix mechanics, that's the place to go. Dirac, of course, first relativistic quantum mechanics. Landau and Lifshitz, a very important quantum mechanics textbook. John Bell, by the way, translated that from for Landau from the original Russian. Messiah, very important quantum mechanics 2-volume set that I used at Columbia. Unfortunately, he's not totally stuck in the second school. He actually flip-flops a bit in his interpretation and jumps between the lab space and the configuration space description. Pauling and Wilson, Linus Pauling from Caltech, of course. This is what all the chemists use. And the granddaddy of them all, von Neumann's mathematical foundations of quantum mechanics. This is where he generalizes configuration space into Hilbert space. Of course, David Hilbert was his thesis advisor. Okay. It is formulated, the second school of thought is formulated in configuration space. What is configuration space? It's an abstract, k-dimensional vector space. What's a vector space? It's one set of numbers that depends upon another set of numbers. That nothing more, nothing less. That may or may not say anything about geometry. Configuration space is just such a vector space. This is Hilbert space. It's used for specifying the configuration of the system that you're studying. So it was originally introduced actually for classical mechanics, for Hamilton-Jacobi theory of classical mechanics, which I studied here at Caltech out of Goldstein's book. Okay, so unlike lab space, the structure of configuration space depends on the system that you're studying. The number of degrees of freedom depends upon the system that you're studying. Particles' degrees of freedom are not dimensions of space-time. Okay, so in configuration space, we have the wave function psi as a function of just k degrees of freedom. This is straight out of von Neumann's book, if you like. Okay. And Schrodinger's second equation now describes the evolution of this configuration space wave function. So say, for example, you're studying helium. You have wave function psi is a function of x, y, z, x1, y1, z1 for particle 1, the spin of particle 1, discrete values plus minus. Okay, x, y, z of particle 2, the spin in particle 2. Wait, we've now got 8 arguments here. Remember that lab space had 3 dimensions. This cannot be lab space. Okay, so the wave function, even more important, this wave function cannot depend upon the position in the lab where you measure it. Remember, that's what we all agreed on, or I thought we sort of agreed, that psi of R and T define the value of the wave function and the probability density at every point in the lab. It is totally independent of the lab vector. If you tried to include it in the argument string, it would violate transformation theory. Remember, one of the tricky bits of quantum mechanics is you can talk about coordinate representations and how these basis transformations between momentum and position representations, that's all done with transformation theory. If you stuck in an additional value of R lab, you would be adding a hidden variable. Okay, so it means that psi star psi and psi are independent of our lab. That means they have the same value everywhere in your lab, unlike the lab space formulation. Okay, so Born's was the first to actually produce what I call Born's ambiguity, where he claimed that these two were equivalent. They're obviously not equivalent for the reasons I have just stated. There are very few textbooks even noticed this difference. Dickey and Whitkey, my favorite book, and Merzbacher both expressed grand alarm over the fact that you cannot have waves propagating for a helium atom. There's no waves, probability waves propagating in space. And that's as far as they got. And more importantly, the Schrodinger's equation, if I reduce for n particle system, if I take the special case with n equal to 1, does not reduce to Schrodinger's equation in lab space. Okay, so configuration space is necessary for providing quantum mechanical description of multi-particle systems. It is the source of entanglement. Any rational formulation can't really change the space you're operating in just simply by changing the number of particles you put there. So therefore, one really needs to consider for hydrogen that we are in a working in a one-dimensional configuration space. Okay, so the configuration space has its own problems. First off, it does not describe geometry. So our beloved Green's theorem, Gauss's theorem, Stokes' theorem that we learned to describe the geometry of lab space do not apply in configuration space. But so you cannot derive conserved probability currents. Landau and Lifshitz and Messiah don't even notice, and they just proceed to do so anyway. Nobody ever notices. No, it tries to explain, what does it mean? If someone here can tell me what it means to have a flow of a current in this mathematical, purely mathematical abstract vector space, I'd like to know, how do I visualize it? I am unable to. Einstein was unable to. Merzbacher was unable to. So this is what I view as a serious difficulty, and which is what makes quantum mechanics virtually impossible to really understand. There are other problems, like for example, with configuration space. Von Neumann points out there's a very unhappy essential weakness, what he calls, of configuration space. It is that it's not inherently a relativistic formulation. For the you can't do Lorentz transformations in configuration space, just like you can't have Gauss's theorem or Green's theorem calculated. And moreover, for each particle, you're only talking about X, Y, and Z for the jth particle in the system, but not T for it. To be fully relativistic, each particle carries its own clock. If the particles are moving at high speed relative to each other, each one's clock proceeds at a different pace. So Bethe and Salpeter, in their book on quantum mechanics of 1 and 2 electron, they ran into similar difficulties for calculating the relativistic corrections to the spectrum of helium. Okay, one calculates the Dirac's equation is for hydrogen, the equivalent two-particle equation, a relativistic equation for helium is the Bright equation. It is not, Bethe and Salpeter point out that it is not truly relativistically invariant. Okay, so we can't. What's wrong? We can't visualize a flow in an abstract. We can't make conceptual models in this abstract mathematical space. And so I find that this means that it's almost impossible to, for at least for me and for Einstein, to understand quantum mechanics. So how did this resolve the Einstein-Bohr discussion? They were really talking past each other in their, Bohr was assuming quantum mechanics was to be formulated in this configuration space. Einstein was assuming quantum mechanics was really formulated in lab space, and neither of they both bought Bohr's ambiguity, which said they're really the same thing. They are not. Okay, so since it's a totally artificial mathematical space, there is no propagation, no prohibition of propagating signals faster than the speed of light. So all of Einstein's problems with superluminal communications between the two detectors disappear. Why not? Okay. So the locality, Einstein's locality arguments were totally disappeared for Bohr. This instantaneous collapse of the wave function, which appears to propagate faster than the speed of light, that disappears because there's no limit to the propagation of signals faster than the speed of light. Okay, so, well, I think I'm probably out. Am I still have any time left or? Okay, so here's a minor amusement, if you will. Okay, so as I noticed with the Messier satellite, we have huge range over which one can demonstrate entanglement over 1,000 kilometers by the Chinese Messier satellite. So Messiah's quantum mechanics textbook shows that if two particles are independent and do not interact, they are unentangled and they will remain unentangled as long as they don't interact. The converse is also true. If they ever interact, they become entangled and they remain entangled. Spitzer points out, at least for classical, one thing I ran into in when I was working on plasma physics, that the classical Coulomb cross-section for scattering between any two charged particles is infinite. It diverges, the differential cross section diverges at small scattering angles. This is why in plasma physics, when you're studying this, you have all these damn log lambda cutoffs you have to do to arbitrarily cut off this interaction. Bottom line of this is that all charged particles in the universe, all widely separate, no matter how widely separated, interact with each other, which means they are all at least a little bit entangled. So, and we know from Schrodinger evolution that entanglement will grow exponentially in time. So here is the basic quandary. Being a little bit entangled is sort of like being a little bit pregnant. The importance of both conditions depends on how long you wait. So, final quandary is, remember, I mentioned that local realism is dead, that but general relativity is a form of local realism. So what does the demise of local realism say about general relativity? It says, well, we've seen that general relativity needs to somehow be general relativity is formulated in lab space, clearly. The warping of lab space occurs because of the finite mass of stuff, of matter, that has a finite mass density. But that's all lab space formulation, not configurations. So one needs to somehow build a configuration space extension of general relativity. I have no idea whether or not that's possible. For example, if you warp space enough, you get a black hole. Can you quantize the spin of a black hole? Can you get if you have black holes in definite spin state, can you entangle them? And will spin measurements of the pair of black holes, is it possible that they would violate a Bell inequality? I have no idea what the answers to these questions are. I will end with that. Sure.
We have time for questions.
Fine. Sure.
Here to defend his honor.
Sure.
Einstein is not here to defend his honor.
Yeah,
But I would say that I'm very confident that for 40 years he was trying to understand what the photon is.
yes.
And if anybody thinks that he understand what the photon is a fool. So my question really is.
Well, that was part of the pointing out. That was not at all clear. That was one of the big disputes effectively between Schrodinger and Einstein. Are these things, are these photons? Now, in quantum field theory, they are and far the best description of this is done by Fermi in a Reviews to Modern Physics article. This was Feynman's starting point for quantum electrodynamics, but basically one, I'm sorry, let me finish. Oh, you finish your question.
Because I understand your reluctance or your proof that photons cannot be put in a box.
Yes.
And it's obvious that then when you have entanglement, then the Bell inequality has to be, it's violated by nature. But what about real particles? I mean, you can't really get particles like atoms. You can't put particles far away enough that you can exclude local hidden variables.
Yes.
So they interact.
Oh, indeed. Experiments have been done doing exactly that. And the way that is typically done is by entanglement sharing. This is a trick that Zeilinger developed, where you could have two remote, for example, atoms or ions held in a trap that one can take a pair of entangled photons and then propagate them to these independent and then put the two ions into an entangled spin state. This is quite possible and has been done. And in fact, people are able now to entangle superconducting qubits, big things, whole clouds of rubidium atoms have been entangled with each other.
Maybe we can talk after.
Sure. But yes, it is quite possible to do this. When I first started doing this, I pointed out that no, you couldn't do the experiment with a pair of baseballs. It would be very hard, and nobody has, to my knowledge, no one has entangled the spin states of a pair of baseballs. But let alone a pair of black holes. But I theoretically, as far as I know, there's no prohibition for that.
I'd like to ask what current or future quantum experiments are you excited about? Or
Me, I'm retired.
What do you recommend?
I don't have any experiments at the moment to recommend. Sorry. Yeah, I don't know.
First, we need to learn. So,
But yeah.
I really enjoyed listening to your presentation. So one question I have was, are there any non-local hidden variable theories?
Sure, but why, like Bohm highly have a non-local hidden, but why bother? Why not just use quantum mechanics? You can't, they would require somehow communication faster than the speed of light. Okay, now here's the argument against that. And this is in the back of Bohm's book on special relativity in an appendix. And this gives rise to what's sometimes referred to as the grandfather paradox. Can you travel back in time and kill your father or kill or kill your grandfather so before your father was born, so that you couldn't possibly be born, therefore you could not travel back in time? And the way Bohm did it in the textbook is, and you can look this up if you want, he has 4 observers, A, B, C, D, and they're all moving with respect to each other. And A sends a signal to B, B sends a signal to C, C sends a signal to D, and D sends the signal back to A in a total loop. Okay, if you suppose A asks a question that C answers. So what Bohm shows is you can always arrange if at least 2 of the, I think it was 2 minimum of these communications need to be superluminal, faster than the speed of light. If you could send signals for these 2 communications faster than the speed of light, and all the 4 observers are moving relative to each other, you could always arrange a situation where the D's message back to you arrives before you send the first message, and you reverse the time order of the events. So you don't like the answer that C gave you, so you ask a different question. The question is history single value? The basic assumption for here for the prohibiting faster than light communication or non-local hidden variables, etc., which could include A, B, and C, and D, or for the components. The basic assumption is that such absurdity, this is a reduction to absurdity, if you will, argument, saying that no, you can't, that history is always single value. It's quite conceivable that nature being in a multi-valued state is what a superposition of a quantum superposition is. I really don't know. It's a pure speculation.
Thank you.
I have a simple question.
Good.
If the photon travels through, say, a crystal, it's going to separate it into two entangled photons. What is the photon experiencing? What causes it to?
Good question. And the bottom line is nobody knows. And that is the essence of Bohr's argument, is that there is no description. You're asking about what does it, you're effectively saying the same thing that I was saying. You're asking, what does it mean to propagate in this mathematical k-dimensional vector vector space? I haven't the foggiest. If you could tell me, let me know.
So it's a good question.
Oh, Einstein asked it, you betcha. And Bohr said, there's no answer. If you're saying, okay, here I am. Okay, this is what Bell in this original paper was considering. Suppose here I am in one of these Stern-Gerlach apparatuses, and I need to figure out, all right, here I just have this spin a half atom coming at me. Which beam do I send this into? What Bell showed is you can't do it and still get the cosine distribution. That was the grand revelation of Bell's theorem, that it's impossible to do that. So if you have a little man in there, your Maxwell demon or whatever, trying to sort these photons or spin half particles or whatever particles you're using, he or she cannot do it, period.
Ask one more.
Sure.
Can you describe the collaborative process with Michael Horne of Richard Holt in developing the CHSH inequality?
Okay. Originally, I had this. I was trying to understand quantum mechanics. I ran across. I flunked quantum mechanics course you had to get a B in at Columbia several times just because I couldn't understand any of this, and was trying to understand it and ran across Bell's paper. And when I was a graduate student at Columbia, I started working on this whole question, much to the distress of my thesis advisor. I was supposed to be studying, doing quantum mechanics calculations of scattering of cyanide molecules for my thesis was on cosmic microwave background measurement. But so my thesis advisor was outraged at how you're wasting all your time doing this, but nonetheless, finally thought it was very interesting. So I published went to a Washington APS meeting and published a bulletin article, and I immediately got a phone call from Abner Shimony that he and Mike Horne, Mike Horne was his graduate student, and they, and he said, "You've scooped us. We're working on exactly the same problem and have come up with exactly the same solution." Basically, I was proposing that the Kocher-Cummins experiment, which was the first measurement of the polarization correlation in the calcium system, that be extended. So we got together in Washington and basically compared notes and decided we really need to publish this together. So we joined forces and published. This is the CHSH paper. Oh, and it was this outraged the faculty, the theory group at Columbia, because I didn't ask their permission to do this. So, but anyway, so that's kind of how CHSH got written.
Just check the online question. Raising hands. Sure. There's one question.
Oh, we got lots of questions.
All right, so a lot to talk. Okay. You can ask your question. Yanis?
Yes, hi. So from what I understand, there is a transformation for one spin per session from the lab stage to the configuration stage. But you said this can be for more than one particle, like more than one spin, it's not possible.
Sorry, we cannot hear
I can't
you.
understand.
So can you, did you type your question? We cannot hear you. Did you type your question in the chat? Oh, yes. Is a transformation for one spin from lab space session to configuration space for more than
You cannot transform. That was Born's ambiguity. You cannot transform from lab space to configure. Yes, in transformation theory, you can transform your basis states from configuration in, for example, momentum space to coordinate representation, if you will, within transformation theory. But you cannot bring in lab space. It's a totally different concept, and it is not part of lab space. Is not a component of configuration space. So once you are in a multi-particle system, and I argue multi-particle can include the special case of one particle, you must stay in configuration space, which means you cannot use lab space.
Okay.
I hope that answers your question.
If there are more questions we can answer maybe later, but
Okay.
maybe only one
Okay.
more. Is
Yep.
it possible to for quantum teleportation?
I am not the expert on quantum teleportation. I wouldn't. Okay. In Star Trek, one steps into a quantum teleporter quite readily. I wouldn't. Here you have a telephone booth or whatever. You step into this, and you are told that every particle in your whole body will be torn apart and disappear. And somewhere else, a replicant who has all your memories will be walking around. Would you do that? I wouldn't.
Okay.
But and no one, all that really Zeilinger's work has done for quantum teleportation is to teleport effectively a single particle's quantum state. So,
Thank you very much.
Okay.
Thank you.
thank you.
For this great talk, and it was amazing. Okay, thank you everyone. We have about 10-15 minutes for until the next talk. Okay, thank you everyone.